Okay, welcome to the MIRTEC booth here at IPC Apex Expo. Delighted to be joined by Brian D'Amico. Good to see you again.
Pleasure as always to see you too.
I know, it's been a while. I mean, you were on a panel discussion this morning and here we are today.
I did miss you though.
Yeah, there you go. So, a couple of new machines here this week, Brian. The first one here is the ART, which is an anti-reflective technology.
Yes.
So, explain to us a little bit about how it works and how you've actually, I think you've enhanced it even since it first came out.
Okay, very good. So what we have here is a 5-camera system, but all 5 cameras are being used to collect 3D information.
Okay.
It is actually the world's first 75 megapixel 5-camera 3D system.
Right.
Normally, right, normal configuration, you'd have maybe a single top-down camera, 4 projectors, right, for projecting the light pattern down onto regions of interest or a frame, and all of the 3D data is collected by the top-down camera. What we now have, next evolution of this, and it is truly a game changer, is that we now have 4 additional cameras, 4 additional 15 megapixel cameras that are collecting that 3D information.
So you've got 4 side cameras, one at each side, and then you've got one top-down.
Exactly.
Okay.
And the purpose of that really, if you're talking about just having a single top-down camera, there's really 2 things that may happen with the data. One is you can get some saturation, that's light that's basically being reflected back into the camera, like shiny spots, right? Another that you get is also blind spots. So if you have maybe, if you're projecting down onto a solder joint and you have a tall device, the body may prevent some of that information from getting back into the top-down camera. So it's kind of almost shadowing the data going back to the camera.
So how do you get around that? How do you deal with that?
So now we have, with this system here, we've got 5 cameras. So basically the top-down camera, whatever information can't make it to the top-down camera is now being picked up by the side cameras.
Okay.
So we're actually merging together all of that data. This is kind of like basically what it comes down to is this. Everyone here, all of the AOI systems on the floor here, including ours, what we're basically doing is when we have blind spots or we have light saturation, we have to work with that data. We have to filter that out. We perform high-end algorithms to basically take that data, and we're modifying, right? Modifying the data to make the image look as best as possible, and it's mostly an educated guess as to exactly what the data looks like. When we have like saturation, where we have like a hole in that data, where data is missing, right? So that's basically cooking the data, right?
Of course, yeah.
Then we have the sushi principle, which is basically raw data. So if you ask your accountant, raw data versus cooked data, raw data is going to win. Right. So ultimately, we're dealing with the best possible data solution, all raw data. Right. And you could basically see a very, very big difference when we're talking about that, right? So rather than having to use an algorithm to modify that data, we're using raw data to provide the best quality 3D image and the best quality 3D inspection of the boards. Okay.
So raw data, so basically what you're literally getting, you're seeing the image exactly as it is without any kind of interference, any kind of change at all.
Exactly.
So show us an example of raw data. Is this a raw data image we're looking at now?
So right now we're talking about a raw data image using our ART system, and that raw data image is actually, you can see it's very clean. We see the solder fillet very clear. Yeah. And the difference would be we can switch this over to where we have the ART turned off. And once the ART is turned off and we collect that data again, you'll be able to see that there's some information here that we're actually missing. Right. So what we're doing is a raw data analysis with ART turned on and raw data analysis with ART turned off. Okay. And you'll see a very big difference between the two.
Right. Okay.
And so what you're looking at here, Trevor, is now with the ART system turned off. So now we're just using the single top-down camera to collect the 3D data. Yeah. And keep in mind, this is non-filtered data. This is raw data. That's all we're displaying here. So you'll see here with the raw data displayed that we have some missing information. Yeah. And that would be caused by either light saturation or perhaps having a blind spot where some of the light is trying to get back into the top-down camera, but you're going to see where the data is actually lacking. Right. So
the data is lacking, so you couldn't accurately measure that meniscus there.
Exactly. So that's where you'd have to use algorithms to filter out that information, or actually to fill in the information, quite frankly. And once again, all AOI, all SPI, that's pretty much the way they work, right? You're dealing with high-end algorithms to help filter the data, fill in some of the missing data, etc. But realistically, what we want to do is deal with pure raw data and give you the best possible inspection results. Right.
So as you get down into these smaller geometries for like semiconductor and things like that, does that become more important?
Absolutely. That's when this is a real high-end system. When you start dealing with very, very small devices, very small pads, you want as much accurate data as possible. Yeah. What you really want to be doing is you want to be doing less filtering. You want less algorithms. You do want pure raw data at that point here because you have less of a margin, less pixels for you to inspect to determine whether or not you have a good solder joint, good bad solder joint, etc. And that's where it really becomes critical to have, once again, pure raw data.
Okay, excellent. So, I mean, we were talking this morning about the topic of AI and how it can help short circuit some of the work that the operator has to do. Would that work in this case using raw data as well?
Well, when we're talking about AI, mainly we're talking about images that are captured, right? So on our systems here, there's several different reasons why you'd be using AI. One is if you are trying to classify defects, you can collect a lot of data to determine whether or not the defect should be classified as, say, a missing component, missing solder, etc. So it's basically just data that gets stored together in a database for defect classification. Another thing, for instance, on our conformal coating system, we have bubble inspection, right? So our Genesis CC does bubble inspection. There's a lot of images that we put into that system to determine whether or not you've got bubbles present or not. For looking at lead tips, this system uses AI in order to look at lead tips. So we have several different images of lead tips. And what we do is we use that to determine where the lead tip is, right? So that we can measure the solder joint at the end of the lead tip. So typically AI is typically in combination with big data images that are captured. This system here is basically, instead of doing that, we're actually just doing pure measurement. So it's a little bit different than using AI to look at multiple different images.
Okay, got it. Okay, so while we're here, we're going to take a look at another machine that you've got that measures actually very tall components.
Exactly.
When I say tall, I mean, I think the biggest I've seen in the market so far is like 50 millimeter, and this goes beyond that. So
this will do up to 70 millimeters.
70 millimeters. Let's take a walk around and take a look at it.
Okay.
So Brian, here we are at the TAL Component system. The first thing I notice when I'm here is it says MV6 OMNI. So you got an MV6 OMNI sitting here, but another, the TAL 3D scan is a unit that bolts onto the side of it.
Exactly. So what we have here is this. So the TAL 3D scan module, and that's basically stands for TAL Component Analysis Laser. That's a laser-based system. And what it's used for is it's used in tandem with the MV6 OMNI. So what we're able to do is inspect all TAL devices with the TAL 3D scan unit. And once the board passes through that module and we scan anything over 25 millimeters, basically, we're able to scan and pass that defect data to the MV6 OMNI. The purpose of this is to increase the speed. Actually, it increases productivity by about 30%. So when we put the board into the TAL 3D scan, we can inspect anywhere from, say, 5 millimeters up to 70 millimeters tall. Then the board gets passed over to the MV6 OMNI. So when we're talking the MV6 OMNI, this is our standard MV6 OMNI machine. We've got 3 different frequencies that are capable in that system. From 0 to 5 millimeters, we use 2 frequencies. From 5 to 25 millimeters, we use the 3rd frequency. That 3rd frequency for dealing with some larger devices, taller devices, slows down the system a bit as well. Anything, of course, over 25 millimeters, we really would have to move the head. And when we move the head up and down, that will slow down the system as well.
So how does the laser work? Is the laser working from a top-down perspective, or is it working horizontally too?
No, it's basically a top-down laser, right? So with anything else, you of course require an angle of incidence. So you have an emitter and you have a receiver. And actually, I'll open this up and show you the way it works. And this way here, you can kind of see that as well. But basically, what we end up doing there is we scan across the board, and it's just a laser. It's a laser that can scan across the entire board, not a point laser. It's a scan laser. Then that 3D information gets passed over to the MV6 OMNI, and the MV6 OMNI does not have to do any inspection of any TAL devices. So that's the whole thing. But now keep in mind, the way it works as well, for productivity purposes, we've got a board that's being inspected in the TAL 3D scan and a board being inspected in the MV6 OMNI. Once the board in the 6 OMNI leaves, the next board comes in from the TAL 3D scan. So realistically, any inspection that's done by the scan system, by the TAL 3D scan module, is 0 overhead, right? 0 inspection time. Because while that board is being scanned, the other board is being processed by the 6 OMNI. So we're really doing parallel processing of PCBs through the line. We're not just doing parallel processing. I mean, because this doesn't have to move up and down in any way, it's working at optimum speed. Exactly. And that's the whole thing. So for automotive applications, say you have boards with a lot of taller pin devices on it, or any tall through-hole devices, this machine is excellent for that. That's what it's geared towards. If you look at maybe a laser-based system, because those systems are used for looking at maybe pin devices, right, automotive, but you only have about 3.5 inches of scan, right? So basically you have to, for doing a 15 millimeter tall device, you'd have to do maybe 4 or 5 scans across the board, moving the head each time.
Yep.
So it slows it down tremendously.
Yep.
So this is truly the world's fastest system for dealing with taller devices.
Yeah.
Yep.
All right, so Brian, I mean, here, you know, we're looking now at an image here, which is showing the tall device here.
Yep, so basically this is the result of the TAL 3D scan module. We've scanned the board,
right,
and all of these boxes here are the tall devices that are on that PCB.
Okay.
And this is the information, this is the resulting information from the TAL scan module.
Got it.
So basically all of these tall devices, all of that information now is passed over to the MV6 Omni. So all we do on the MV6 Omni right now is we use 2 frequencies. We don't have to move the head up and down to capture any of this data. And so that's going to be the fastest way that we can run the MV6 Omni. We do not have to test any of these tall devices. All of that data is automatically brought into the 6 Omni.
Right, so this image here really reflects what's happened here in the TAL 3D scan. Once you then finish your scan in the MV6, that additional data will be added to this.
Exactly, exactly. Okay. So it's like almost having 2 machines in one, quite frankly.
Yep. Yeah, absolutely. Yeah. Great. Well, it's a very innovative approach to doing tall device measurement, and a great way of keeping up with line speed.
Absolutely.
Or even better.
That's exactly what it's designed for, Jeff, right?
Yeah, so congratulations, and thank you for showing it to us today.
Yeah, it's a beautiful machine. Thank you for taking a look at it. I appreciate it.
Okay.